Welcome to College Physics 1. For Chapter 1, we're going to dive into the nature of science and physics. Physics is one of those sciences that you kind of see it everywhere without necessarily thinking about it. It's in your everyday lives. Pretty much anything that you can think of has some type of physics logic behind it. So in this course, you'll see that a lot of the laws that we have in place for physics can kind of be applied to just things that you don't necessarily think about. But for this chapter, we're just going to introduce everything, some of the concepts and some of the definitions that you'll be able to use along the way for the rest of the semester, and just some of the small details that will definitely appear. So as far as physics is concerned, with describing the interactions of energy, matter, space, and time, and it is especially interested in what fundamental mechanisms underlie every phenomenon. The concern for describing the basic phenomena is nature essentially defines the realm of physics. So for physics, we have different things that occur, and there is an explanation for basically everything that happens. So here in figure 1.1, you see a galaxy where, so many things are going on, and for these billions of things, billions of natural occurrences that are happening, we have an explanation for every single one of them. For here, figure 1.4, you see a basic microwave. The laws of physics help us understand how common appliances work. For example, the laws of physics can help explain how microwave ovens heat up food, and they also help us understand why it is dangerous to place metal objects in a microwave oven. We know that it's very dangerous if you place certain things into a microwave, but we have certain formulas and certain laws that will pretty much tell you why exactly that is. So for these two applications of physics have more in common than meets the eye. Microwave ovens use electromagnetic waves to heat food. Magnetic resonance imaging, MRI, also uses electromagnetic waves to yield an image of the brain, from which the exact location of tumors can be determined. So they're still both electromagnetic waves, but they have different uses of them. One is obviously to heat up food, and the other one is for imaging. So one one aspect of physics can be used in several different ways. So models, theories, and laws. A law uses concise language to describe a generalized pattern in nature that is supported by scientific evidence and repeated experiments. So we'll go through several laws during the semester, where you'll see us build a case for that law, and we'll pretty much prove it one way or another. A theory is an explanation for patterns in nature that is supported by scientific evidence and verified multiple times by various groups of researchers. So basically, theory you can think of as like your hypothesis in an experiment, something that you just have to prove because you know that it's true and you have to figure out a way to prove it. And a model is a representation of something that is often too difficult or impossible to display directly. While a model is justified with experimental proof, it is only accurate under certain situations. Easiest example for that would be anything in space or anything subatomic. Things that we can't see with our own eyes, but we know it's out there, and we have formulas and explanations in place that pretty much explain what's going on, that far out in space or that small in our world. So for here's a model. This planetary model of an atom shows electrons orbiting the nucleus. It is a drawing that we use to form a mental image of an atom that we cannot see directly with our own eyes because it is too small. So we know that they exist. We know that we have atoms, we have electrons, protons, neutrons, and so on. And we know that there's models of them, but it's not something we can actually look at. The laws of nature are concise descriptions of the universe around us. They are human statements of the underlying laws or rules that are all natural processes follow. Such laws are instinctive to the universe. Humans did not create them, so they cannot be changed. We can only discover and understand them. Models, theories, and laws are used to help scientists analyze the data they have already collected. However, often after a model, theory, and law has been developed, it points scientists towards new discoveries they would not otherwise have made. So basically, it's saying, okay, well, we found, let's say, this proton. Well, we know that it's being pulled by something. We know that there's a force pulling it or pushing it. So that way they found like their neutron or their electron and so forth. It's not, just they don't solve the whole puzzle. They just know that they're solving pieces of the puzzle. And from there that they can find the next piece and the next piece and the next piece. So the scientific method, which is something that we will use in this class with the labs, as scientists inquire and gather information about the world, they follow a process called the scientific method. So they have observation and question. So they observe something happening and they question it. Why is this happening? Where is this going? What is making this happen? 2, research and hypothesis. They research, what they know, and they make estimated guess about it. 3, they test it, see if their theories are right and if they're not. And then 4, they analyze whatever results they get. Not necessarily, you won't get the result you're looking for on the first try or the second or the third, but they'll analyze every single result. So that way, for their next test, their next hypothesis, they know exactly whether which direction to go to. So physics as it develops from a Renaissance to the end of the 19th century is called classical physics. It was transformed into modern physics by revolutionary discoveries made starting at the beginning of the 20th century. So limits of the laws of classical physics. For the laws of classical physics to apply, the following criteria must be met. Matter must be moving at a speed less than 1% the speed of light, so something that we can observe, and the objects dealt with must be large enough to be seen with a microscope. Only weak gravitational fields, such as field generated by the Earth, can be involved. Modern physics itself consists of 2 revolutionary theories, relativity and quantum mechanics. So basically, classical physics is something that you can observe with your own eyes. Something that, you don't need to have assumptions or, just something that you can observe. Whereas modern physics kind of deals with, quantum level theory and, space. So classical physics is just kind of, your cars, you have your, throwing a ball, something we can observe. So for physics, we define a physical quantity either by specific how it is measured or by stating how it is calculated from other measurements. For example, we define distance and time by specifying methods for measuring them, whereas we define average speed by stating that it is calculated as distance traveled divided by the time of travel. So that's one of the main points that we're going to get started with. Measurements of physical quantities are expressed in terms of units, which are standardized values. For example, the length of a race, which is a physical quantity, can be expressed in the units of meters for sprinters or kilometers for distance runners. So here's where we dive into units. We start seeing something that we can measure with. There are 2 major systems of units used in the world: the SI units, also known as the metric system, and the English units. It is an intriguing fact that some physical quantities are more fundamental than others. They can be defined only in terms of the procedure used to measure them. The units in which they are measured are thus called fundamental units. In this textbook, the physical quantities are taken to be length, mass, time, and electric current. So electric current we won't deal with, but for length, you have your meter, which is M, and from there you can go to kilometers, centimeters, so on and so forth. For mass, you have kilogram. Same thing, you can go to grams. For time, you have seconds. You can still use minutes, hours, even days, years. And like I said, for electric current, we won't use, but for the fundamental unit, it is an ampere. All other physical quantities, such as force and electric charge, can be expressed as algebraic combinations of length, mass, time, and current. For example, the speed is length divided by time. So we use 2 of these fundamental SI units to get your speed. These units are called derived units, and trust me, there's going to be a bunch of these in the later chapters. So the second, the SI unit for time, has a long history. For many years, it was defined as 1 divided by 86,400 of a mean solar day. More recently, a new standard was adopted to gain greater accuracy and to define the second in terms of non-varying or constant physical phenomena, because the solar day is getting longer due to very gradual slowing down of the Earth's rotation. Cesium atoms can be made to vibrate in a very steady way, and these vibrations can be really readily observed and counted. In 1967, the second was redefined as the time required for 9,192,631,770 of these vibrations. Accuracy in the fundamental units is essential because all the measurements are ultimately expressed in terms of the fundamental units and can be no more accurate than the fundamental units themselves. So basically, all they did was make the second more accurate. Like they said, it's a fundamental unit. So just like your meter is 1 meter, they needed to make sure that the second never varied, that it wasn't always changing. And like I mentioned earlier, the way they expressed it before was because of the Earth's rotation. Now they have a different way of expressing it, something that is finite, something that will not change over the course of time. The meter is the SI unit for length. Its definition has also changed over time to become more accurate and precise. The meter was first defined in 1791 as 1 out of 10 million of the distance from the equator to the North Pole. This measurement was improved in 1889 by redefining the meter to be the distance between 2 engraved lines of a platinum iridium bar, now kept near Paris. By 1960, it had become possible to define the meter even more accurately in terms of wavelength of light. So it was again redefined as that number, wavelengths of orange light emitted by krypton atoms. In 1983, the meter was given its present definition, partly for greater accuracy, as the distance light travels in a vacuum, 1 over 299,792,458 of a second. This change defines the speed of light to be exactly that same number, meters per second. The length of the meter will change if the speed of light is someday measured with greater accuracy. So we know that this has a chance of changing, but it's only going to change to be more precise, basically. So here in figure 1.19, the meter is defined to be the distance light travels in 1 over 299,792,458 of a second in a vacuum. Distance traveled in speed is speed multiplied by the time. So here you see this flashlight. In that short time, that's what 1 meter will be. So now to the kilogram, the SI unit for mass. It is defined to be the mass of platinum iridium cylinder kept with the old meter standard at the International Bureau of Weights and Measures near Paris. Exact replicas of the standard kilogram are also kept at the United States National Institute of Standards and Technology, or NIST, located in Gaithersburg, Maryland, outside of Washington, D.C., and at other locations around the world. The determination of all masses can be ultimately traced to the comparison with the standard mass. So, metric prefixes. SI units are part of the metric system. The metric system is convenient for scientific and engineering calculations because the units are categorized by factors of 10. So, the order of magnitude refers to the scale of a value expressed in the metric system. Each power of 10 in the metric system represents a different order of magnitude. For example, 10 to the 1, 10 to the 2, 10 to the 3, and so forth are all different orders of magnitude. For example, the number 800 can be written as 8 times 10 to the second, and the number 450 can be written as 4.5 times 10 to the second. Thus, the numbers 800 and 450 have the same number of magnitude, 10 to the second. Order of magnitude can be thought of a ballpark estimate for the scale of a value. The diameter of an atom is on the order of 10 to the negative 9 meters, while the diameter of the sun is in order of 10 to the 9 meters. So we see one has a positive 9 and one has a negative 9. That makes a big difference when you're talking about size. Here is the metric prefixes chart. As you can see, you have prefixes exa, peta, tera, giga, mega, kilo, so on and so forth with their respective value, 10 to the 18th, 10 to the 15th. And you have your examples right there, set it up. And on the very right column, you can see where they kind of get relative. So the first one is distance light traveled in a century. Peta would be 30 million years. Tera would be powerful laser output, so on and so forth. So you have some examples at least to follow on where these would be used. So you see here on 10 to the 0 would be basically your meter, if you want to think about using the SI units already. So for our first topic, we'll talk about dimensional analysis. Some of you may remember this. You might have seen it in another class. So it is often necessary to convert from one type of unit to another. Let us consider a simple example of how to convert units. Let us say that we want to convert 80 meters to kilometers, km. So the first thing to do is list the units that we have and the units that you want to convert to. In this case, we have units in meters and we want to convert to kilometers. Next, we need to determine a conversion factor relating the meters to kilometers. So we know that meters is the base unit and we want to switch to kilometers. You can go back to this chart and see that kilometers here is 10 to the 3. So a unit conversion factor is a ratio expressing how many of one unit are equal to the other. For example, there are 12 inches in a foot, 100 centimeters in 1 meter, 60 seconds in 1 minute, and so on. So those are your ratios. In this case, we know that 1,000 meters is in 1 kilometer. So first you'll have your 80 meters times 1 kilometer over 1,000 meters. That is your ratio. That is your conversion factor. What you notice here is that the meters cancel out because you are multiplying a meter times a kilogram or a kilometer and then dividing it by meters. You have to make sure that your old units cancel out. So the only units that are still existing are your new units. So here, once the units cancel out, you have 80 times 1 divided by 1,000. If you put that in a calculator, you'll get 0.080 kilometers. Okay. But another thing you can notice here is that we know that 1,000 meters is 1 kilometer, correct? So if we go back to this chart and see that 10 to the 3rd, well, 10 to the 3rd can also be written as 1,000 meters. So there's another way you can figure out your conversion factor. Okay, so for our first example, suppose that you drive the 10 kilometers from your university to home in 20 minutes. So we have our distance and we have our time, or let me say our length. So calculate your average speed in kilometers per hour. So kilometers per hour is our units there, and B in meters per second. So M over S, meters per second. Note that the average distance traveled divided by time of travel. So this is our first formula. Average speed equals average time, or equals distance over time. So another thing I do want to point out, all these examples will be in the textbook. This is something that would be easy for everybody to track going through the textbook, seeing these examples because they are covering the lectures as well. So here is the same problem that we were talking about. So if you go down here, well, we have our distance over time, correct? So we have distance, 10 kilometers, over our time, 20 minutes. So that'll just be 0.5 kilometers over minutes. So for here, convert your kilometers per minute to kilometers per hour because the question did ask for kilometers per hour. So here we have kilometers per minute, so we have 0.5, that's our number with this. Times, we need to find a ratio. So we know that 60 minutes is 1 hour, right? And we want our old numbers, our old units to cancel out. So minutes over minutes cancels out. So we have kilometers left here and an hour left here. So you end up doing 0.5 times 60. That'll give you 30 kilometers per hour. And that is the answer to A. So for B, now we're trying to find it out in meters per second, correct? So for B, you come down here, you have your kilometers per minute times 1 hour over 60 minutes. So this will be essentially what you're going to be using. But we come down here, we have our average speed. We know that we already solved it for 30 kilometers per hour, right? But now we want the kilometers to be meters, and now we want the hours to be seconds. So our conversion factor for hours would be 1 hour equals 3,600 seconds. You could also do it by parts. You could do 1 hour is 60 minutes, and then do 60 minutes divided by your seconds on, or your 1 hour divided by 60 seconds, and all your conversions would be canceled out there. But this is a direct conversion anyway, the 1 hour over 3,600 seconds. So that'll be our conversion for our time, correct? Because the hour here and the hour here will cancel out. So now we have to worry about our kilometers. Or, well, what we do know is 1,000 meters is 1 kilometer. So we easily cancel out the kilometers right there. So now you just multiply straight across. So you have 30 times your 1,000 on the very right side. And you also have to divide by the 3,600 seconds. So that'll give you an average speed of 8.33 meters per second. And that'll be your answer for B. So all that just came from knowing that we have our 10 kilometers and we have our 20 minutes. We just did 2 problems right there where we just had to convert units, and we also used our equation here for average speed to solve the problem. You could have done it separately as well if you wanted to. You could have changed everything, talking about your 10 kilometers. You could have changed that to meters if you wanted to first, your 20 minutes into seconds first, and then done the equation. So it kind of just depends on which way you want to go. With physics, there's not just one way to solve it. So there's 2, 3, sometimes 4 different ways to solve it. So if it's easier for one person to solve it differently than another person, go for it, obviously. So now we're going to talk about accuracy, precision, and significant figures. So accuracy is how close a measurement is to the correct value for that measurement. The precision of a measurement system refers to how close the agreement is between repeated measurements. So your accuracy would be, if you're actually, let's say you're driving, I say I'm going 60 miles per hour, but I'm actually going 58. That's your accuracy. Because I know I'm not going 60, but I'm going 50. I could say I'm going 59 and it's somewhat closer to 60. It's just because it's getting closer and closer to what I'm actually going to. Your precision would be if I keep saying I'm going 60, now I'm going 58, 59, 61, 62. So how close I am to the exact number after repeating it so many times. So the degree of the accuracy and precision of a measuring system are related to the uncertainty of the measurements. Uncertainty is a quantitative measurement of how much your measured values deviate from the standard or expected value. If your measurements are not very accurate or precise, then the uncertainty of your values will be very high. And this is something you will definitely use in some of the labs coming up. You want to get your numbers as precise as possible. So we will go into an equation here shortly that you will be using for sure. So for here, an archer attempts to shoot the center of a bullseye. The black dots represent each attempt to hit the center of the target. The dots are spread out quite far apart from one another, indicating low precision. So if he was hitting the same spot, his precision would be high. But if he's hitting all these 4 different spots, it's low. But they are rather close to the actual bullseye, indicating a high accuracy. So we know that the point of this is to hit the very center of the target. Now, if he keeps hitting, let's say, this spot right here on the right side all 4 times, and his accuracy is high and his precision is high. But if he's hitting something outside on this red circle, on the outer circle, high, his precision would be high, but his accuracy would be low, because the point of it is to be hitting the center of the bullseye. So in this figure, just like I mentioned, the dots are concentrated rather closely to one another, indicating a high precision, but they are rather far apart from the center of the target, indicating low accuracy. So here is where we're talking about uncertainty. In more general terms, uncertainty can be thought of as a disclaimer for your measured values. For example, if someone asked you to provide the mileage of your car, you might say you have 45,000 miles plus or minus 500 miles. So in this situation, let's say you actually have 45,550 miles. You're going to say I have 45,000 miles. The plus or minus amount is the uncertainty in the value. That is, you are indicating that your actual mileage of your car might be as low as 44,500 miles, or as high as 45,500 miles, or anywhere in between. All measurements contain some amount of uncertainty. One thing that you will notice as we go through this course is uncertainty can be coming from different directions. It's not just something that deals with numerical values. It could be human error. For example, there's been a lot of occasions where if you're doing an experiment, and let's say you're trying to figure out the uncertainty values here or of that experiment, you'll see that it's not just directly pointed at the numbers. Sometimes it's because certain things are happening within the experiment that you can't control, or like I said, human error is a big one most of the time. It just kind of depends on where it's coming from, but it's not always directed to the numbers. So uncertainty, the factors contributing to the uncertainty in a measurement include: 1, limitations of the measuring device; 2, the skill of the person making the measurement. So that would be like, human error, like I mentioned. 3, irregularities in the object being measured. So maybe it's changing why it's being measured. And number 4, any other factors that affect the outcome, highly dependent on the situation. So it kind of, like I said, uncertainty can come from different directions. It's not just something that can just be based off the numbers. It could be like number 1 said, limitations of the measuring device. Like let's, for example, say like you have a ruler. If you're not placing that ruler at the exact same point every single time, then that's uncertainty of the measuring device. The ruler can only measure, however much you want, but if you're not placing it at the same point, it's gonna be different every single time. So percent uncertainty. One method of expressing uncertainty is as a percent of the measured value. If a measurement A is expressed with uncertainty, and then the change in A, that's what that symbol means, the percent uncertainty is defined as that equation right there. So it's kind of like your percent error, basically. So you're changing A. So let's say you're aiming for one number, but you got a higher number. So the difference there divided by the number you're actually supposed to get times 100% would be your percent uncertainty. So if you have something that's supposed to measure 5 meters, but you measured 6 meters. So let's say you'll have 6 minus 5 over 5. That'll be 1 over 5 times 100%. And that 20% is going to be your percent uncertainty. Okay, so for example, 1.2, a grocery store sells 5-pound bags of apples. You purchase 4 bags over the course of the month, and the weight of the apples each time. You obtain the following measurements. So for week 1, you got 4.8, week 2, 5.3, week 3, 4.9, week 4, 5.4. You determine that the weight of the 5-pound bag has an uncertainty of 0.4 pounds. What is the percent uncertainty of the bag's weight? So we see that the numbers change constantly, but it's not always the same number. And he's trying to figure out what the percent uncertainty would be based off that fact. So, like we mentioned, we're going to use that same equation. So percent uncertainty. So we know that the change in the expected number, so we have A, our change in uncertainty is 0.4. That'll be what our change in A is, 0.4 over our expected value, which is 5. We expect the bag that says 5-pound bag of apples to be 5 pounds of apples. So times 100%, we can see that our uncertainty percent uncertainty is 8%. So it's not that very high, but we know that there's going to be some type of difference every single time that we go buy apples. Okay, so that brings us to significant figures. An important factor in the accuracy and precision of measurements involves the precision of the measuring tool. In general, a precise measuring tool is one that can measure values in a very small increments. For example, a standard ruler can measure length to the nearest millimeter, while a caliper can measure the length to the nearest 0.1 millimeter. The caliper is more precise measuring tool because it can measure extremely small differences in length. The more precise the measuring tool, the more precise and accurate the measurement can be. So for here, you have, using the method of significant figures, the rule is that the last digit can be written down in a measurement is the first digit of the uncertainty. So for here, A, B, C, D, E, all 5 of these have different significant figures. We know that 6, let's say for C, 6 times 10 to the third, just because it's 6 times 10 to the third doesn't mean the number is going to be 6,000. Okay? So just because A, for example, 0.009 doesn't mean there's not a number behind it. So there's always an uncertainty every single time we have significant figures. That's why whenever we're doing an experiment or we're measuring something, or we're doing a problem, it's important to have the right significant figures every single time. Because if you don't, then we're going to have numbers that have 5 sig figs. That's short for significant figures. 5 sig figs, 4 sig figs, so on and so forth. So the uncertainty is going to get bigger and bigger because we know that we're missing some values here. So for A, it has 1 significant figure. The zeros in this number are placekeepers that indicate the decimal point. So we see that these 3 zeros here are just placekeepers. For B, here we have 6. The zeros indicate that a measurement was made to the 0.1 decimal point, so that the zeros are significant. For C, we have 1. The value is 10 to the third, signifies the decimal place, not the number measured values. For D, we have 5. The final 0 indicates that a measurement was made to the 0.001 decimal point, so it is significant. And for E, we have 4. Any zeros located between the significant figures in a number are also significant. So we know that if by A and D, they say that they had zeros here following the 9 and this other 0, we know that there was measurements made to that smallest 0. Yep. So for number 1, for multiplication and division, the result should have the same number of significant figures as the quantity having the least significant figures entering into the calculation. For addition and subtraction, the answer can obtain or contain no more decimal places than the least precise measurement and a number that is exact, such as the 2 in the formula that are for the circumference of a circle, c equals 2 pi r. It does not affect the number of significant figures in the calculation. So these are 3 rule of thumbs whenever you're dealing with significant figures. In this class, most numbers are measured to have 3 significant figures. Furthermore, consistent numbers of significant figures will be used in all worked examples. You'll notice that in the text that an answer given in 3 digits is based on input good to at least 3 digits, for example. If the input has fewer significant figures, the answer will also have fewer significant figures. Care should be taken so that the number of significant figures is reasonable for the situation posed. So for approximations, on many occasions, physicists and other scientists and engineers need to make approximations or guesstimates for a particular quantity. What is the distance to a certain destination? What is the approximate density of a given item? What is the volume of a lake? Many approximate numbers are based on formulae in which the input quantities are known to be limited accuracy. These approximations allow us to rule out certain scenarios or unrealistic numbers. So it's just approximations. We tend to make approximations every single day. Let's say you are driving to work and you're approximating it's going to take you, 30 minutes versus 25 minutes today because, traffic is a little bit heavier, or, if you're making a meal, it's going to take you a good 25 to 30 minutes, depending on what exactly you have to do. So we do approximations every single day. So it's basically the same concept here. Okay, for example, 1.3, can you approximate the height of one of the buildings on our campus and in your neighborhood? Let us take an approximation based upon the height of a person. In this example, we will calculate the height of a 39-story building. So the strategy here is to think about the average height of an adult male. We can approximate the height of a building by scaling up from the height of a person. We go down to 1.3 here. All right. So we know that one person here, an average male, is 2 meters. And we know that each story is about 2 persons, people. And we're trying to find 39 stories. So we know that here, our unit of measure is 1 person, and it's also 2 meters. But we know that 2 persons equals 1 story, so the person to person here cancels out, right? We're also trying to find 39 stories, and we know that 2 persons equals 1 story, so our stories here cancel out. So eventually we just have meters. So here we have 2 times 2 times 39, which will yield 156 meters. So this is your approximation. It's still the same way of finding your answer based off like the average speed formula that we used earlier, but it's just a different way of solving it. All right, going back to PowerPoint. Okay, so here for figure 1.27, the U.S. federal deficit in 2008 fiscal year was a little greater than 10 trillion. Most of us do not know any of that concept of how much 1 trillion actually is. We're just approximating. We're just using numbers that are given to us based off those numbers on the fiscal year. So for here, suppose that you are given $1 trillion in 100 bills. If you made 100 bill stacks and use them to evenly cover a football field between the end zones, make an approximation of how high the money pile would become. We will use feet and inches rather than meters because football fields are measured in yards. So again, we're approximating how much money it would take to reach to fill up a football field here. Okay, so here we calculate the volume of stack of 100 bills. The dimensions of a single bill are approximate, so they're about 3 inches to 6 inches, let's say. A stack of 100 of these would be 0.5 inches thick. So the total volume of the stack of bills is the volume of, let's say, a rectangular prism. So length times width times height. So you get 9 inches cubed. So we know that each stack is 9 inches cubed, let's say. Calculate the number of stacks that you'll need. So note that the $1 trillion is equal to 1 times 10 to the 12, 10 to the 12 being trillion. And a stack of 100 bills is equal to 10,000, so 1 times 10 to the 4th. The number of stacks you will have is 1 times 10 to the 12 divided by 1 times 10 to the 4th. So you'll have 1 times 10 to the 8 stacks. Okay? So now you got to calculate the area of the football field in square inches. So the area of the field is 100 yards times 50 yards, 100 yards being the length of the football field and 50 yards being how wide it is, which gives you 5,000 yards squared. Because we are working with inches, we know that we have to convert square yards to square inches. So here we use our area that we found and we do a conversion to get us into inches squared eventually. So we have yards squared. We know that 1 yard is 3 feet and we have to do that twice because we have squared yards. We want to get to inches, so we have to do 12 inches as 1 foot twice, so we can get inches squared. So our area here is 6 times 10 to the 6 inches squared. So the conversion gives us that number. So here we have 9 inches cubed divided by the stack times 10 to the 8 stacks. So we know we have to cover 9 times 10 to the 8 inches cubed here. So now we calculate the height. So the volume of the bills equals the area of the field times money of the height. The height of the money we know is volume of the bills over area of the height. So now we plug in the numbers that we actually found. So we know we have volume of the bills, which we just found, is 9 times 10 to the 8 inches cubed. And we have area of the field, which is something we calculated here, 6 times 10 to the 6 inches squared. So we end up with 1.33 times 10 to the second inches. But like we mentioned earlier, we have to be careful with significant figures. So this ends up being 1 times 10 to the second inches. So that approximately is about 8 feet. So that's how high the stack of money would be to cover up the football field. All right, and this is just a basic summary of chapter 1. We went over the introduction to physics, some of the physical quantities and units. We went over some SI units, what the actual SI units were for length, mass, time, accuracy, precision, and significant figures, and approximation. So these 4 subsections will be pretty important in the coming chapters. They will be used pretty common. So please get familiar with them, especially the SI units and the significant figures. Those will be very common throughout the semester. And it's something that you have to have a good grasp on so you don't miss a few points here and there on, let's say, a quiz or an exam because you used the wrong significant figures. So please contact me if you have any questions. And please review the homework and quiz that are corresponding to this chapter.